the Tampere University of Finland, and his talk is about non-uniform stability of damped contraction semigroups. So you can start.
Thank you very much for the introduction and the opportunity to speak here. So today I'm going to talk about the joint work with my co-authors listed here. And we have a preprint on this topic, so I will also link that to the chat so you can take a look at it during the presentation if you like. In this talk, we are interested in the dynamical properties of this second order differential equations of this form shown here on a Hilbert space H. And in particular, we are interested in finding conditions on these two operators L and D, which would guarantee the stability of this equation in the sense that all solutions of this equation converge to zero as in norm as t goes to infinity. And also we're interested in studying the rate of this convergence. And throughout the talk, we assume that the operator L here is a self-adjoint positive and boundedly invertible operator. And then on the other hand, the operator D in this velocity term here is a bounded operator from another Hilbert space U into H. And our results also contain a generalization to the situation where D is an unbounded operator, but I'll mention this a little bit later. So for now, D is bounded. And perhaps the most important PDE model which fits into this abstract framework is the n-dimensional wave equation with viscous damping, which involves this kind of a damping function as a parameter. So a non-negative valued function, which is a parameter of the spatial variable. And we know that under suitable conditions on the especially the boundary of the spatial domain, we can indeed put this into the abstract form, and Dirichlet-Laplacian is a positive operator. And then on the other hand, the operator D can be defined as a multiplication operator, pointwise multiplication operator based on the damping function D. And in this conference, we also know that quite well that the second order equation can be written as a first order abstract Cauchy problem with an extended state on this kind of a product space. And in this situation, our semigroup generator has the form of A minus BB star, where this A generates a unitary group on X, and B minus BB star is a dissipative perturbation. So in total, this operator generates a contraction semigroup on X. And we're interested in the stability of our second order equation in the form where these norms shown here converge to zero for all initial conditions. And the reason for considering these norms comes from the first order abstract Cauchy problem representation, where this is the norm of exactly the norm of the extended state of the first order problem. But another motivation for considering this type of a norm is also that for many PDEs, these norms are exactly proportional to the square root of the energy of the solution of the PDE. For abstract differential equations, there are several different notions of stability with different kinds of properties. And in this presentation, we're especially interested in the so-called non-uniform stability, as well as its special case of polynomial stability. And these stability types are defined in the form shown in the way shown here. So the norm of our solution is bounded by some term, coefficient term here, which decays to 0 as t goes to infinity. And the rate of this decay is determined by this increasing and unbounded function m. And then we have another term which only depends on the initial condition. And the characteristic feature of non-uniform stability is that this rate of decay is only required to hold for classical solutions of the equation. So when the initial data is a little bit more smooth than for mild solutions. And likewise here in the decay estimate, we have the graph norm of the initial condition instead of its regular norm. And non-uniform stability can be compared especially to strong asymptotic stability, where we would have decay for all mild solutions, but we wouldn't have any guaranteed rate for this decay. And on the other hand, to the stronger form, the exponential stability, where we would have exponential decay also for mild solutions. And non-uniform stability, the motivation for the study is that non-uniform stability arises as an encountered in several types of PDE models, especially damped hyperbolic models such as wave and beam and plate equations, in situations where the damping is either somehow weak or it only affects relatively small portions of the domain. And in addition, non-uniform stability is also investigated very actively in the context of coupled PDE systems. And I happen to know that Filippo is going to talk about this next. So hope you stay and hear his talk as well. And in our 2D PDE example, the wave equation, this non-uniform stability is understood fairly well. And here the type of stability for the equation depends very heavily on the damping parameter d, the damping function, and especially on the so-called damping region, which we can define as the set where the function d gets non-zero values. And very roughly put, the equation is going to be exponentially stable if the damping region is relatively large. And on the other hand, in situations where the damping region is relatively small, we instead always get non-uniform stability for our abstract differential equation. And there's also a well-known condition, so-called geometric control condition, which distinguishes between two cases. And this condition precisely tests whether or not all the rays reflecting, traveling inside the spatial domain and reflecting optically from the boundaries of the domain meet the damping region after some given time, or alternatively fail to do so. And this test, the outcome of this test tells us whether or not we get exponential stability or non-uniform stability for our equation. But here, this example is mainly to illustrate that there are several types of several cases and very typical cases where we actually get non-uniform stability for this PDE model. So this is indeed a worthy topic for investigating. And in this talk, my main aim is to introduce some new fairly general conditions which can be used in proving non-uniform stability for PDE models and also deriving the exact or approximate rates of decay for this that is associated to the stability type. And as I mentioned, the motivation comes from the fact that many hyperbolic PDE models are shown to be non-uniformly stable, and this is investigated very actively in the literature. But on the other hand, there still is quite a lot that has to be done on a case-by-case basis in this when this is done. And what our main interest is to add some general, fairly high-level tools into the toolbox, which can be used to show that certain given PDE models are non-uniformly stable. And I'll also mention that the non-uniform stability has been investigated very actively in the context of semigroups, and there are very general and powerful results available, which reduces the question of non-uniform stability to the obtaining of resolvent estimates for the semigroup generator on the imaginary axis, and these results really form the basis of our work here as well. And in this talk throughout, we're interested in this kinds of observability type conditions for the stability, and these involve the operators L and D of our equation. And this is also this approach is something that we didn't arrive at by accident, but instead there's a long history and tradition in relating stability of abstract Cauchy problems to certain types of observability properties. And this goes back to, in the infinite dimensional setting, to at least the work of Marshall Slemrod in the early 70s. This work showed that exact observability in a suitable form is equivalent to exponential stability. And on the other hand, the generalized work shows that also approximate observability with suitable additional assumptions becomes closely related or equivalent to either weak or strong stability of the semigroup. And in our work, we're interested in non-uniform stability, which sits somewhere between exponential and strong stability. And on the other hand, our results here relate the stability properties to generalized observability conditions, which can be seen as forms of non-uniform observability. And this kind of work also has been done previously earlier in the literature as well, especially by Amari with several co-authors. And our results in part generalize these works, and also in part they take parallel paths to those investigations. And going into my main results of the talk, I just want to mention again that we have this recently accepted paper, and which contains quite a large number of different types of results in this kind of a same area and similar nature. So I invite you to take a look at the paper for a more detailed coverage. But here I'm only focusing on two results taken from that paper, and in that sense, this is more like an advertisement for our preprint than it's not intended to be a full coverage of what we've done. But the first condition I want to introduce here is kind of is defined as an observability type condition shown here. So this is a parameterized inequality involving the operators L and D, as well as a scalar parameter S, and this should hold for all S. And in addition, this condition involves two non-decreasing functions, M0, which may be increasing and unbounded. And this is indeed an observability type condition because the form of this inequality is familiar from this so-called Hawthorne's test type conditions, which are used very often in classical literature as tests and for observability types, for observability properties for dynamical systems. And the reason why this is a generalized observability condition is that we allow these functions M0 to be unbounded, and whereas in more classical versions, they would be either constant or bounded functions. But our main result related to this Hawthorne's type condition is that if L and D are such that this condition holds for some functions M0, then our abstract differential equation is indeed non-uniformly stable. And in addition, we also get a specific rate of convergence for the classical solutions of our equation. And the way we get this rate of decay is that we define this function capital N, which involves the parameter functions M0 from the Hawthorne's test, as well as an additional quadratic term. And once we do this, then the rate of decay for classical solutions is determined by the algebraic inverse of of the function n. And because the growth properties of n and its inverse are closely related, we can especially observe that if n grows relatively slowly, then correspondingly the inverse grows relatively fast, which makes the decay of the solutions relatively fast as well. And especially if n is bounded by a polynomial of S, then the solutions decay at least rational rate. And correspondingly, if n grows very quickly, for example, exponentially, then the decay of the solutions may be quite slow, for example, logarithmic decay. So the second condition and the second type of observability condition I want to use and introduce involves the spectral projections of the positive operator, which is the square root of L. And here I'm using the square root only in order to keep the formulas fairly nice, because of course the spectral projections of the square root have one-to-one correspondence with the spectral projections of L itself. But the condition we want to investigate involves testing the lower boundedness of the adjoint of D when we restrict this operator onto the spectral subspaces of square root of L. And the more specifically, the way we do this is that we take a scalar parameter S, and then we take spectral interval for the square root of L with radius delta. And this delta here, the radius, is allowed to depend on the point S, which is with the center of the interval. And then we indeed restrict D star to the spectral interval, and we test whether or not this restriction is lower bounded. And this lower bound that we get, the possible lower bound we get, is also allowed to depend on the point S. And if this lower boundedness is true for all values of S, then we say that our operators L and D satisfy this so-called wave packet condition. And again, here, because we allowed the spectral radius delta and the lower bound gamma to be dependent on the parameter S, these delta and gamma are in general functions of S, which may be non-increasing, and typically in an investigation of non-uniform stability, at least one of them will be a decreasing function, which goes to zero as S goes to infinity. And our main result related to this wave packet condition is that if L and D satisfy this condition for some parameter functions, delta and gamma, then our abstract differential equation is again non-uniformly stable. Again, we also get a rate of decay for the classical solutions, and this time it's determined by the algebraic inverse of another function, capital N, now defined by or dependent on the parameter functions, delta and gamma, which appear in the wave packet condition. And similar conditions apply, similar comments apply on the relationship between the growth rate of this function N and on the decay rate of the solutions as well. So, as I mentioned, these were a couple of choice results from our paper, and in the paper we also especially developed the similar theory for first order systems which have the same form as our abstract Cauchy problem, but we also deal with the more general situation where A is merely a generator of a contraction semigroup, so it doesn't necessarily need to be a group. And we also deal with quite a technically challenging situation where the operator D or operator B can be an unbounded operator instead. And the nice thing about this setting, more general setting, is that it allows the study of wave equations with damping on the boundary as well, and study of their non-uniform stability. Okay, and to conclude my talk, I want to consider a few types of examples of PDEs and discuss what our results say about those. So, as I mentioned, non-uniform stability has been studied for two-dimensional wave equations quite actively in the literature already from the 70s, and this is understood quite well. There are several results which can be particular results that can be reproduced by our results, new results, and which have a slightly generalized form, but this is by no means all of those results that are already known for this equation. And to be fair, a lot of these investigations that have been done previously have already been using this kind of approach of observability type estimates, and even abstract operator theoretic methods have been used. But there are also some references which particularly aim at deriving these generalized types of observability estimates, like the ones in Berg and Zuili. And some of these works have not yet previously been linked to the stability properties of the equations. And in these situations, our results can be used as a bridge to link the observability estimates to the stability properties of the damped equation. And finally, there's a lot of interesting and nice things going on in the two-dimensional damped wave equations, and these all that contains a lot of interesting phenomena, which can also be used in investigating the optimality of our results. And especially it's been shown fairly recently and in several references that the smoothness properties of the damping function D can radically improve the stability properties of the damped equation. But on the other hand, the smoothness properties are very often invisible to the types of observability conditions which we investigate and use in our work. And this creates a kind of a inherent suboptimality when it comes to applying our results into the, especially to the two-dimensional wave equation. And on the other hand, our results can be used also for simpler models, such as one-dimensional wave and beam equations. And in this situation, the viscous damping always leads to exponential stability, but these kinds of weak or non-local dampings, which act in an averaged manner, produce non-uniform stability, and in our results can be used to study these types of damping very effectively. And in these one-dimensional models, we have shown in our paper that our results also lead to optimal results. And finally, I want to also mention an interesting application of our results from a recent paper by Pei Su, Marius Tuxnak, and George Weiss, where the authors were using our results to investigate a stabilization problem for this so-called water wave system. So the system models small amplitude water waves, and it's a two-dimensional coupled Pdes system with boundary control. And the authors were doing control design and using our wave packet condition for showing that the stabilized system is polynomially stable. And one of the reasons why I think this is an interesting situation is that the undamped system and its generator have quite curious properties and somewhat atypical properties, and especially you have the spectrum doesn't have a uniform gap. It's a simple spectrum, but the eigenvalues behave like square root of k when the k goes to infinity. And in this setup, our wave packet condition, the ability to choose our parameter delta, can be used in quite an effective way to investigate the...
Could you give us a chance for questions?
Yeah, sure. This is my last slide. Sorry. Yeah. So they were using this wave packet condition with decreasing delta, and this is a nice way to investigate this stability. So this concludes my talk, and I'm definitely happy to answer any questions. So thank you.
Thank you. Okay, so we have some time for questions, remarks. Maybe I ask about something you consider a Dirichlet problem here, yes? So if you change the boundary problem, for example, you have derivative, that the normal derivative is 0 at the boundary. What about such a situation?
Yeah, I think it shouldn't matter. It just changes in the abstract setting, it just changes the operator L. So what you would aim at is just verifying this type of an observability estimate for that modified operator with different boundary conditions. But as I mentioned, this is a little bit like a high-level tool, so you have to be able to understand your operator and your differential. So this is the undamped differential operator, and this is damping. So you have to have a good understanding of both of those and their interplay in order to use these results. So
another question, remark.